Okay, cool. So we've got a data set of images that we made. When we create that, we can return items by indexing which element from that data set we want. At the moment, there is no transform. I've set that as default to none, so this block isn't being run, and it's returning us the image that it opens using PIL, which is Python Image Library. So I'm just going to keep this as a template. I'm going to delete those last 3 lines. This is our dataset class. Now I'm going to make a new file. And I'm going to call this model. And now I'm going to show you how to actually create a machine learning model. So yeah, to start off with, let's import that dataset that we just made. So we'll import the dataset file there. We'll import Torch. It's PyTorch. We'll also do from Torch Vision import transforms. And that gives us some transforms that we can apply to our data to change it into different format, namely from a PIL image into a torch tensor, which we can put into our model. So yeah, we'll probably come across a few more as well. But the way that we're going to do this, so firstly, we're going to get that data set. So we're going to say dataset is equal to, that file is called dataset. So we'll say dset is equal to dataset dot image dataset, like that. And then if we index that, we can get files from it. Yeah, in fact, let's say we'll print the first element from that. Run this, and then we get a filter. Delete this line. I don't want to be printing the file paths when I'm running this model. So yeah, now we run that. We get a PIL image from our dataset when we do that, right? Now, we actually don't want a PIL image. We want a torch tensor. So we're going to say that my transforms is equal to torch vision transforms dot compose. And so what this does is composes a list of transforms. So open list with square brackets, and then list all the different transforms that you want to apply to your data when you get it. So we're getting it in PIL form, and we want to change it into a torch tensor form. One other thing that we might want to do to ease computation is to resize it. So we can say the first transformation that we want to apply to our data is transforms.resize. This takes in a tuple of the size you want to take it to. So let's take it to 64 by 64. Next item in the list, i.e. next transform that we want to apply, is the one that's going to take it from a PIL image to a torch tensor, so to tensor, like that. Now we can pass this. We can pass this into our model here. Just remember, is it transform or transforms? Transform equals my transforms. Okay, cool. So now if we run this, we won't get a PIL image. We'll get a torch tensor. So this is a torch tensor. That's our input, which was that image, but now it's had this transformation applied to it. So now what we're going to do is we're going to create a data loader. So a data loader is a way of batching together several examples so that you can pass them to the model all at once. And also it has handy features for shuffling our data set so that we're not learning, we're not repeatedly, every time we go over the data set, we're not learning this at the beginning and forgetting it by the end. We're shuffling all of that around so that we don't tend to have learned away from the examples we saw at the beginning of the data set, because they're always going to be different every time we go through it. So yeah, so we're going to create a data loader. So well, firstly, we want to split our data set into training, testing, and validation. So we'll say from torch.utils.data import random split, and then we can say training data, validation data, testing data is equal to random split of the data set we had, and then the sizes which we want to take those data sets into. So I've just got like a trivially small data set here, like a jokingly small data set. So I've only got 11 images. So I'm going to come back here. I'm going to say, imagine this were larger, and you could compute these numbers automatically, but I'm just going to say, okay, I want 7 images in my training set. I want 3 in my validation set, and I'm going to have 1 in my test data set. Okay, cool. So now we split the data set into 3. 1 we're going to train on, 1 we're going to use to adjust the hyperparameters, and then 1 we're going to actually test on without having seen any of it before to see how well we're doing. So the next thing we'll do is create a data loader for each of these objects. So I'll just create a training data loader. So I'll call it train loader. Yeah, from torch.utils.data we'll also import data loader. There you go. So we'll create a torch data loader. What this takes in is the data set, which it's going to be loading from, which in our case is train data. Then we can tell it to shuffle true, and we can say batch size is equal to whatever we want. So let's say batch size of 4. And you would do the same thing for validation and testing. Now we've got the data set. We can load it in batches. Now we're going to create the model. So we'll actually create a class called, in this case, I'm going to implement like a simple an autoencoder. I'll explain what that is in a sec. So yeah, explain what that is now. So an autoencoder takes in some input, and it tries to output the same as the input. The only thing with this is that between those two layers, where we have, in this case, 64 by 64 features and 64 by 64 features output here, those are the sizes we resize the image to. In the middle of this model, there's less than that many features. So it's a bottleneck inside the model. So we basically have the data, we encode it, and then we decode it again. And when we're encoding it, we're trying to, we're forcing the model to find a lower dimensional representation of this image. And then using that low dimensional representation, we're going to try and get it to reconstruct the output. And to do that reconstruction, it will help intuitively if our model learns to represent the example with meaningful features in the bottleneck. So they're going to be high level features like, how bright is this image? What's the rotation of this image? Those kind of things. Things that we don't see looking at these numbers right here. Like we don't see them in the data. We see them when we abstract from the data. And so forcing this bottleneck forces the model to learn meaningful features, and then is going to mean that there are abstractions of the actual low-level data. There'll still just be numbers like this, but they will be forced to mean something more complex and ideally useful. So we're going to create this autoencoder. It's going to inherit from torch.neural network module, so that we can do some stuff like call the parameters function, so we can get the parameters to get to the optimizer, and some other handy stuff which just makes it easy to build models. So we'll initially we'll initialize it like this. So constructing this autoencoder, what we'll do is we'll say that, like I said, it's got two parts. It's got an encoder and a decoder. So we say that self.encoder is equal to torch.nn.sequential. Torch.nn.sequential basically allows you to list within it the repeated layers that you want to apply to this, that you're going to apply when you call this object. So it returns a callable object. So this self.encoder, I can call it. That is, I can put brackets on the end of it and give it an input. I'm going to give it an input image like this, and then it's going to output me an encoding. How's it going to do that? It's going to pass through several layers sequentially. So what I want those layers to be are, I'm going to say the first layer I want to be torch.nn.2D convolution. So check out the CNN theory I did. And what this layer takes is the number of channels that are coming in. This is an RGB image, so it's going to take three channels, that is RG and B, and then I'm going to say, okay, how many channels do I want you to output? That is, how many one channel activation maps do I want you to output? Each of those activation maps comes from looking for one particular filter all over the image. So in other words, this out channels, the number of activation maps is a number of filters which I'm going to convolve over the image, and that is the number of different features that I'm looking for at this first layer. So let's say 64. Then we'll go, okay, now what do we want to do? We need to remember to add an activation function. Then what we'll do is apply another convolutional layer, and this needs to take in. So now the input to this has been transformed into 64 channels. So this needs to take in 64 channels. Then how many channels we're going to do from that? Let's say 32, whatever. And then we'll say torch.nn.relu here. So activate our input like that. Okay. And a comma there. Okay, so that's our encoder. Then we'll say self.decoder is equal to similar kind of thing. Torch.neural-network.sequential, sequentially applying. Now this time we don't want to do convolution which decreases the size. We actually want to do deconvolution. So it's basically it's kind of like you can think of it as the inverse of convolution. So instead of compressing an image down, it's going to try and expand it back up. And I'll cover that in theory later if that's not clear. Otherwise I'll put some links to it. So yeah, we'll do torch.nn.conv2D transpose. Conv2D transpose. Cool. So this is going to go from 32 channels to 64. And then we're going to apply an activation function. And then we're going to again do a transpose convolution, torch.nn.conv2D, conv transpose 2D from 64 now to 3. Okay, so we've encoded our input down, and we're going to now decode it back up. Then what we're going to do is we're going to apply torch.nn.sigmoid in this case. So all of the pixel intensities that you can see from here, they're all between 0 and 1 because they're just intensities. 1 is, 1 in the first channel would be like, this is a fully, the red is its full intensity in this location. So the maximum it can be is 1. So that torch.nn.sigmoid puts all of the outputs that come from this layer within the range 0 and 1. Okay. So now what we've got to define is a forward function. So this is the forward pass of our model, which we're going to pass some input x. What's going to happen when that happens? We're going to perform an encoding. self.encoder of x, and then we'll say x is equal to self.decoder of x. So we're going to encode it and then we're going to decode it. Actually, yeah, just for notation, I'm going to say that z is our encoding of x, and then x tilde, just to be formed with the math, is the decoding of z. Okay, so z is our latent representation. That's our low-dimensional representation, which represents features that we don't see directly in the data, but we just but we can but should be meaningful features that have that show some abstraction of what the actual raw data represents. So then we'll return our x tilde. That's our reconstruction of x. Okay. I'm also going to define here encode x, and that's going to return us self.encoder x, and I'll discuss why we do that in a little bit. Okay, cool. So now we've got the model. What do we need to do now? Now we can try, so now let's create an instance of that model. So I'll say, autoencoder is equal to autoencoder, right? So create an instance of that class called AE. Actually, no, we'll call it model, just for clarity. And then what we'll do is we'll say that we need some criterion to what this is a function which is going to evaluate how bad the model is doing. So we'll say torch.nn.mean squared error loss. Okay, so this mean squared error loss is going to look at every different value in these well, it's going to compare every element in the input with the corresponding element in the reconstructed input. And if they're any different, that means we haven't got a perfect reconstruction. If we haven't got a perfect reconstruction, it means that our model isn't perfect. We're not trying to get it perfect, but we're trying to get it good. And so the larger this number returns us, the worse our model is doing. That's the point of the criterion. It's just a loss function. So then we'll also say we need an optimizer, which we can get by doing torch.optim. One optimizer we're going to use called Adam. What this takes in is the parameters it's trying to optimize. So we can say the parameters, keyword argument, params equals model dot parameters. Now this is a function of model which we didn't define, right? But that's because, as I mentioned earlier, it's inherited from torch.nn.module. So the neural network module gives it this function which it can get the parameters from. This optimizer also requires learning rate, which determines the step size of the updates. So are we going to move the weights by a lot when we update, or only by a small amount? Okay, alright, cool. We have we've got a model, we got a criterion, we got an optimizer. What we're going to do now we're going to create a training function. Okay, what model do we want to train? Yeah, I'm just going to leave that. I'll call it model. Okay, fine. Call that my model. Okay, so my model is an autoencoder, and then this function is going to take in a model, which is going to train. And then it's also going to take in, I'm going to make it say epochs equals 1 to start with. So epochs is the number of times that we're going to go through the whole data set. Okay. So now we're going to go through that data set. So we're going to say for epoch in range epochs. That is for every number in the range up to 1 in this case. If it were 10, then this is going to go first iteration 0, 1, 2, 3, 4, 5, all the way up to 9. So for epoch and range epochs, for batch in the training loader. So remember, our training loader is this data loader, which returns us objects in batches of 4. That's the batch size we defined. So for each of those objects, what we're going to do is we are going to get get our inputs. I mean, it only has one element. Like, there's only one thing in each batch, which is the input, because that's also the label, because we're trying to reconstruct it. So we can just say for x in train loader, and then we can say, okay, we can say x tilde is equal to the model of x. Okay, right. So when we write this forward function, another thing that torch.enum.module does is it sets this forward function to be called when we call our model with arguments, right? So it makes this class callable, and then it will do the forward pass. So when I get this x, what's going to happen is I'm going to encode it and get z, and I'm going to get my reconstruction from the decoder of z, which is just these two things here, right? Okay. I hope the sizes are going to match up, but that's basically the only constraint that we need to worry about. So yeah, let's right. So we've got our prediction x tilde, and we've got our input x. What we're going to do now is we're going to say that the loss is equal to criterion of x tilde and x, right? So that is our reconstruction and the actual true input. What's the difference between those two things? So yeah, and what we're going to do, okay, what we're going to do firstly is we're going to say optimizer dot 0 grad. So basically, the optimizer stores the gradients for each parameter which it's trying to optimize every time it does an update step, but it doesn't reset them back to 0. And when it computes them, it doesn't overwrite them; it adds to them. So if we don't zero the gradients, then they'll accumulate, and they'll never actually be the gradients at that time step for this batch that we're trying to identify the rate of change of the loss with respect to the weights for. So we'll zero the gradients, and then we'll do loss dot backward, and this is a torch function which can be applied on these torch tensors, which also we know how they're computed. That's stored in this object, and then by calling loss.backward, we can differentiate the loss with respect to all of the parameters which it was. Well, we can fill in the gradients for all of the objects which contributed to creating a loss. Okay, and then we can do optimizer.step. So we can do a step and update in our optimizer, right? And then we can print loss is equal to loss. That's loss.item. So loss will return you a torch tensor, lost, but really it's just a single number. Just to get the actual number out of that, we do loss.item. Okay, so is that going to work now? Train my model. Okay, yeah, we're going to run it. Let's see what errors we get. Not implemented error. Okay, yeah. So alright, yeah. So this is because we've actually missed something in the data set. We need to define another function as well just to determine, or just to return the length of the data set. So return the length of self.image file paths. Go back here, run it. What's next? Missing one positional argument, kernel size. Yeah, okay, cool. So I've forgotten all about that. In each of these convolutions, we need to define how big is the kernel. I'm just going to say it's 5 by 5 for all of them. So that's the size of the features which we're looking for in the image, or in the feature map, as long as it's not the first layer. Okay, let's run that. Yep. Let me just try and explain this error. So can't assign module before module.init call. Yeah, what we haven't done is called the parent class. So we haven't initialized this torch.init.module. So super means call a function from the parent class. What function? The initializer function. So this will call the init, the constructor of the parent class. There you go. Right, we're going. So yeah, like this is a trivially, jokingly small data set. I've got 11 examples. It's not going to do anything interesting. But here we have built end to end a model, right? We started off with just files in a folder, and now we've made a data set from them. All we had to do there was tell it how to spin up, tell it how to get me an item when I give you an index, and tell me the length of it. Then we create some transforms to resize it, take it to a tensor from a PIL image. We instantiate the dataset. We split the dataset into training, validation, and testing. We created our data loader. We would have created validation and testing if we were doing this seriously as well. Then we create our autoencoder, which when we set up, we told it how to encode things, how to decode things. Then we defined it, gave it an encoding function and a forward function, which is when I call this object, it does this function. So it encodes it into a latent representation, low dimensional, then it tries to reconstruct from that low dimensional representation. Then what we did, so yeah, we instantiated an instance of that autoencoder. We set up a loss function, the mean squared error loss, to compute the sum of the square difference between each corresponding pixel in the input and the reconstruction. And then we defined an optimizer which told which was going to update the parameters which we told it we want to optimize. We gave it a learning rate to determine the step size. Then we just wrote a training function to train the model for 10 epochs, for epoch in over those 10 epochs, for each input which you get in the training loader. Then make a reconstruction of that by calling the model, which runs the forward pass on X. Then we computed the loss for that example. Then we zeroed the gradients so they don't accumulate. Then we differentiated the loss with respect to the variables which created it. And then we did an optimizer step. Okay. So one thing is, why did we create this encode function? What's actually the point of what we're doing here, right? Okay, the point of our model is not to be able to learn the identity function to take input to what the input was, right? That'll be a perfect autoencoder where we have where we can form a perfect reconstruction. But really, like, what's the point of that? I may as well have just not done anything to the data, and I still have the perfect reconstruction. What we actually want to do is find out how to extract meaningful features from these inputs. So by passing our model through the bottleneck, got a drawing there where it goes encoding and then decoding. By forcing it into a bottleneck, we force it to learn useful things so that it can actually be able to form a reconstruction from it. And so we're learning the salient latent features of this example. And so we should be able to represent this example with a small amount of features which have meaning, right? So now we've trained the parameters of this model. What we can do after we've done it is we can say, you know, okay, I've got a new input, whatever, new input, and then we can say, you know, like the encoding of that new input would be equal to the model of that new input, if that were another image, right? So then this would return us just the, sorry, yeah, we don't want to do my model new input, we want to do my model dot encode, yeah, that's it. So, and then this new input would be some image or some torch tensor which we're passing through. So this would return us the encoding for that, okay? All right, cool. So we'll wrap it up there. But what we could also do as well, just to play around with this, you know, go ahead and try and break this and stuff. We can say like, we can print the loss, not the item. So let's just print that, put some random character there so it breaks, run it, and then now here you can see something interesting, right? So this is our, what was that? I don't know. That's our input firstly. This is the loss, okay, right? So it's a torch tensor, it has this value, that's the mean squared error loss summed over all the pixels, but then it also has this gradient function. And so what this is a record stored alongside the data in the tensor of what the operation was that actually created this number. So that's a mean squared error loss, right? And the point of PyTorch is that, or well, frameworks in general, is that we don't have to write the functions which do the forward or the backward passes, okay? By storing how each tensor was made, we know how to differentiate it quickly, or at least we have a record of it, and we can look up some other function which does that for us. And so all of the intermediate variables in the model, like throughout the layers, they'll have a gradient function as well of how they were created, and by storing that, those are what are called and multiplied together to essentially perform the chain rule when we do loss dot backward. Okay, so that's a bit of how that works. Cool. All right, cut it there.